Yeah. Hello, welcome to our 9 o'clock press conference, the last Arctic sea ice refuge. We'll have 4 speakers. Are you going to be in this order?
Yes. No, in this order.
Okay. And they will be speaking in the order that you will hear just now. Our first speaker will be Stephanie Pfirman. She's the Hirschorn Professor and Department Chair, Department of Environmental Science at Barnard College, Lamont-Doherty Earth Observatory at Columbia University in New York. Our second speaker will be Bruno Tremblay. He's an Assistant Professor in the Department of Atmospheric and Oceanic Sciences at McGill University in Montreal, Quebec, Canada. Followed by Robert Newton. He's a research scientist at Lamont-Doherty Earth Observatory at Columbia University in Palisades, New York. And our final speaker will be Brendan Kelly with the National Marine Laboratory and NOAA at Juneau, Alaska.
Thank you. So I'll be, as Peter just said, I'll be starting out, and I'll be talking about giving you some background on the last Arctic sea ice refuge, and also talk about where we think it will be located. Then I'll turn to Bruno Tremblay, who will be talking about why we think it will be located in this region, and he'll also talk about the seasonality, how large the refuge might be at different times of the year. We'll go from there to Bob Newton, who will talk about where the sea ice comes from that will supply the refuge in the future. And then we'll turn to Brendan Kelly, who will be talking about the ecosystem implications of a refuge forming in this region. I just want to note that there's a couple of colleagues who contributed to this work who are not here today. Charles Fowler at the University of Colorado at Boulder, and also Richard Colleter at the University of Maryland. And I'd also like to note that this research was supported by the Office of Polar Programs at the National Science Foundation. So many of you have seen a chart like this, showing the projected rapid decline of Arctic sea ice. And this would be, the case if global warming were to proceed basically unabated, without mitigation. And what you can see is that there is this rapid decline that's projected to occur sometime in the next several decades, before the end of this next century. But what's really interesting, and what caught our perspective, or the reason why we wanted to look into this, was to look at the tail end of this. What happens after the rapid ice decline occurs, or what happens when the Arctic moves to a largely ice-free state. And what we noticed is that in the models, most models project that there's at least some September sea ice continuing through the end of the century. So we were interested to look into this and to say, where would the ice be located? If it's just patchy and if it's distributed all over the Arctic, then it would be hard to create a viable ecosystem from this. But if it collects in one area, then that could maintain a sea ice ecosystem potentially for decades into the future. So we took a look at where the ice would be located from 2 perspectives. First of all, we looked at current observations indicating where the ice is the thickest, and then we also looked at the models. So to take a look at current observations of where the ice would be the thickest, we're using a proxy for ice thickness, which is ice age. So as the Arctic ice ages, because of ridging and because of annual ice growth, it becomes thicker. And you can see here in this animation, and I'll run it again in just a minute, the red colors indicate the oldest ice. The medium blue colors, or the dark blue colors, indicate the newly formed ice. So on an annual cycle, during the wintertime, you form ice over much of the Arctic basin, but there's only a small band by the end of this cycle, which is 2010, of old ice that occurs right along the margin north of Canada and Alaska. So let me just stop this here if I can. Let me go back. And yeah, let me just, I think it, okay, so we're not going to be able to stop it. Anyway, so you can see that there's large amounts of the red ice that extends over the entire Arctic basin towards the early part of the time series. And that's saying that there's ice that's more than 5 years old that's extending over the entire Arctic. Now watch what's happening. It's diminishing and it's collecting. You see patches of older ice distributed around the Arctic, but right there, you see along the northern flank of Greenland and also of Canada, you can see that there's this ice that's accumulating in a narrow band of where it's the oldest, right here. Okay, so this means that right now the thickest ice is located in this one particular region. And if you take a look ahead, you can see now for what the distribution of ice age was for this past September. And you can see again in the colors, you see a little bit of red, which is older than 5 years, and you see some orange and some green, indicating that this is where the oldest ice is located. Throughout the rest of the Arctic, you see mainly first and second year ice. When you take a look at this distribution, it gives you some indication that this is where the thickest ice is right now. And if you take a look next at the models, you can see that in this projection for 2040 to 2049, this is also where the ice is expected to persist for longest in September. So I'll turn it over to Bruno now to explain more about the models and also about the seasonality.
So the question here is, how do we transition from this climate of today, where the sea ice is quite extensive, like at the end of the summer, to this new climate where what you see here on the right, where the ice is actually reduced and located just north of Greenland and the Canadian Arctic Archipelago. So I'll be showing you an animation that was produced by the National Center for Atmospheric Research in Boulder, Colorado. So this is an animation. Okay, so this is an animation that was produced by NCAR. It shows you the minimum sea ice extent from 1990 to 2040. This is the real world, and soon you're going to be transitioning into the model world. You see the transition is quite smooth, which means that the model is good at producing the ice extent. And you see minimum ice extent only here, animated from year to year with a timeline on the top right. So you can see the transition there in the future is happening like very drastically. You have a very healthy ice cover, and comes a time when you reach a critical ice thickness that is very fragile, like to changes in wind or changes in the radiative budget, and basically you lose your entire ice cover like within a decade or so. I'm going to show it to you one last time. So 1990 to 2049. So you see it's quite extensive, and then the decline occurs. And what you're left with at the end of the simulation is sea ice, which is located just north of Greenland and within the archipelago. So this is the region that we're focusing here on today. This is where we think that in the future there will still be a habitat that will be good for perhaps like some species that rely on ice to actually survive. Okay, so why is it that the sea ice is likely to remain north of the archipelago and north of Greenland? So basically this is just like a cartoon of a circulation of the sea ice in the Arctic Ocean. The black arrows shows like the main sea ice circulation pattern to the Arctic Ocean. What you see is the Beaufort Gyre, which is a circular motion of sea ice, and a transpolar drift stream, which carries sea ice from the Eurasian coast out of the Arctic through Fram Strait. But basically in the central of the Arctic, the main pattern is sea ice flowing from the Eurasian continent onto the North American continent. And the reason is simple, it's because the dominant wind are from Eurasia onto North America. So on the Eurasian side of the continent, the ice is forming, is blown away from the continent, and then forming again and blowing away from the continent in such a way that it always remains very thin in this region of the Arctic. On average, in the winter, you have 1 meter ice thickness in this region of the Arctic. On the Eurasian side. On the Canadian side, where the ice is being pushed and where the residence times is quite long, the ice can get up to 6 and 7 meters on average. So where you have the thickest ice, obviously, when the climate is warming, this is where the remaining ice will stay. So the question that we're asking now is, how free is an ice-free Arctic? We keep hearing on the news like a seasonally ice-free Arctic. Is it free for 1 day during the year, 1 month, 2 months, 3 months, 6 months during the year? This is what we're looking now. This is results from the climate community system model, and we're looking at the seasonality of the ice-free Arctic. So in the center, on the figure in the center, what you're seeing here is in black is the minimum ice extent in today's climate, like 1990 to year 2000. In blue, what you're seeing is the September sea ice extent from in 2040 to 2050. That means like in 40 years from now. So this is the band of ice north of the archipelago which is remaining. Now, if you just go a few months earlier or a few months later, in December and in June, what you see is the black, the blue, and the red, which represents three different time periods, like the 2000, 2050, and 2100, and the changes are much smaller. So you can see that like this ice free is something that is occurring, but it's occurring really in September and the month before in August and the month after in October. But just in June and July and in November and December, the decline and the changes in the sea ice condition are much more minimal. And the question now that we're asking is, what is the impact of the seasonality onto species that lives in the Arctic Ocean? And this is what Brendan is going to be talking to you about just now. Brendan will talk to you about later, but not this is Bob in the meantime, I'm sorry.
So as we started to look at the decline of sea ice and the last place where there would be a refuge, and knowing that the ice collects there because it's essentially blown across the Arctic, we started to look at what are the paths that the ice from the refuge takes to get there. So we started from the refuge and backtracking the ice trajectories back to their sources. And we're able to do this because of a data set that has only been available since about, in 1979, we started having satellite photos of the Arctic region. And by looking at satellite pictures in the microwave band, you can actually, taking differences between sequential photos and using pattern recognition software, you can actually track ice flows from day to day. And using that technique, Chuck Fowler assembled a data set of ice velocities from 1979 to the current. And the transit times up here are anywhere from 5 to 15 years. So it's really just in the last few years that we have enough data to look back and say, where is ice coming from? Where is it going to? What are the transport rates? And the ice, the colors in this chart represent years, and this is essentially looking back from 2008 backwards to say where did this ice track from. And what you can see, this is a picture of from using Chuck's data set. This is looking for the ice refuge region. Where did ice, where did distance ice originate that wound up melting in that region? And this is an analysis we actually did when we were looking at exclusive economic zones. And we were curious, for the Canadian exclusive economic zone, how much ice got in there from, the EEZs of other countries. And you can see that there's quite a bit of ice that comes from Siberia as well as the north slope of the Alaskan region. And what we wanted to do was really, document both the amount of ice, traversing the Arctic, as well as what changes there have been during the satellite era from 1979 to the current. And what we noticed was, well, first of all, the amount of ice transiting the Arctic is quite large. I don't know if you can read the scale on the left, but these are, up there, at the top of these bars that represent the 2000s, you're looking at 100,000 square kilometers of ice coming from the Siberian zone over into the Canadian zone and melting there. And if you look back, if we did this and that, this is everything that moved across the Arctic within 8 years. I mean, we've done a more complete analysis. Obviously, if this was 20 years, you would see that in the 79 and 80, there was also a lot of ice. Not quite this much, but tens of thousands of square kilometers of ice coming across the Arctic from Siberia to Canada and melting there. And in part, so what we're seeing here is both that there's a large volume of ice and that the amount of ice is increasing in the current era. And as the ice pack, there are two effects there. One is that as the ice pack gets thinner and the climate gets warmer, there's less stress within the ice pack and the ice can actually move faster. And we're seeing that the ice is actually moving 10, 15, 20% faster across the Arctic in a warm climate than it does in a cold climate. But the second effect, which is actually dominant in this picture, is that in a warmer regime, every summer the ice pack melts back further to the north and more completely. So that ice that would go from 20 years ago, ice that might go from Siberia to Canada, and actually pass several years in the Canadian zone before melting, and may even pass out of the Canadian zone before melting. Now, in this regime, once it gets there, in the next summer, it's quite likely to melt. So we're having a larger volume of ice, and from Siberia to Canada that melts in the Canadian sector, and that's important because all of the material in the ice is quantitatively deposited in the Canadian zone, or in wherever it melts, and that includes fresh water, which is important for stratifying the water column, and very important for the biology in the surface waters. It includes nutrients and micronutrients, which are any ice that is grown in shallow water will pick up sediments and will leach out both nutrients and micronutrients like iron and deposit those wherever it melts. And there's the potential as well, if there are pollutants in the coastal waters where the ice is formed, those pollutants will be transported and quantitatively deposited wherever it melts. And now I'd like to pass this off to Brendan to talk about some of the biological, ecological implications of all this.
Thanks, Bob. As a biologist, I'm used to the term refuge, referring to some location where organisms survive some kind of interim period. So hearing it used as a refuge of ice, at first seemed a little jarring to me, but I think it's actually appropriate because Arctic sea ice, in fact, supports an entire ecosystem of microorganisms, plankton, fish, seabirds, and mammals, all of which will be adversely affected by the diminishing ice cover. So in the short time I have today, I'll limit my comments to some of the expected effects on the more conspicuous animals. And I hope to demonstrate two things to you. One is that knowing where this ice will persist will be very important in conserving, conserving organisms that depend on that ice. And secondly, that there are features of ice beyond the area it covers. There are other features of ice that are very important as habitat features for animals. What this graphic here is meant to demonstrate to you, I'm simply showing you the number of breeding species of pinnipeds, that's seals, sea lions, and walruses, by latitude. And this is sort of the opposite as you would see in any other group of organisms, and that is that the most species occur at the high latitudes. And this has to do with the fact that for millennia, ice has provided a continental-sized habitat for the seals and walruses. And it's a habitat in which they are, for the most part, safe from predation when they come out of the water to rest, to give birth, to nurse their young, and to molt. So while Antarctic seals enjoy a freedom from surface predators, Arctic seals are in a predator-prey arms race, if you will, with polar bears. Recently descended from grizzly bears, polar bears have become specialists at harvesting marine mammals, particularly seals. And the bears depend on the sea ice cover as a platform from which to harvest those seals. Let's see here to advance. Okay. So one of the ringed seal's defenses from predation is the occupation of snow caves, which conceal them from the bears and other predators. And these caves also provide protection from severe cold. Thus, snow is an important habitat feature for ringed seals. Well, you've heard that sea ice is forecasted to diminish, particularly in the summer months, when within the century it will be limited to that band in northern Canada and Greenland. Thus, the last platform from which bears will be able to hunt seals will be in that region. But how will snow on ice, snow which is critical to the survival of ringed seal pups, how will that change in the coming decades? For ringed seals, the depth of snow in spring months is especially significant. Snow depths have to be at least 50 centimeters in order for the seals to excavate and occupy these layers, these caves in which the pups are born and nursed. When the snow does not accumulate to such depths, the snow caves cannot be formed, or they melt early, and the pups suffer from subsequent freeze events or even from predation by polar bears, Arctic foxes, and even birds. So Cecilia Bitz and I used global climate models to forecast snow depths on ice over the current century. And let's see if I can make this animation work. Should I just do a down arrow? Will that work? Yeah, so over the course of the century, over nearly the entire range of ring seals, snow depths will decrease substantially. And by the end of the century, the portions that will retain snow deep enough for seals to occupy and use these snow caves will in fact be in northern Canada and Greenland area. The implications for the polar bear ring seal arms race of that region being the final refuge for both species is still uncertain. It is clear, however, that this region will be important either as the last stand of these ice-dependent species or as a potential source population to repopulate the Arctic sea ice if it in fact expands in the future, in the distant future. So knowing where the ice and snow will persist at the end of the century is an important starting place for planning future conservation efforts. So I think this work that has been reported today that identifies where this ice refuge will be, is also identifying the refuge for these organisms. And it's really the beginning of what we hope will be an ongoing collaboration between the physical scientists and the biological scientists to look at the conservation effects. Thanks.
Okay, we're ready for questions.
Yeah, Alex Witsy with Science News. My question is for Bruno. We hear a lot of talk sometimes about the ice-free Arctic, and yet Stephanie showed some graphs that showed persistence of some ice. Could you talk a little bit about what the definition of an ice-free Arctic is and how one can have an ice-free Arctic and yet have refuge ice at the same time? I'm just trying to clarify, like, how much is going to be gone and when.
Yeah, that's a good question. Like when we talk about an ice-free Arctic, in 2006 we had a paper coming out and we were talking about a seasonally ice-free Arctic occurring as early as 2040. What we meant by that was it was mainly free. There was still some ice within the archipelago, north of the Canadian Arctic archipelago in Greenland. But for all practical purposes, like most of the Arctic was free of ice, and navigation and all kinds of things like this could be occurring. So it's not like a very clearly defined like concept when we say seasonally ice-free Arctic. What we basically mean is that most of the Arctic Ocean is actually not covered by sea ice. This is what we used as our definition.
If I could just add to that, it's an important distinction because people keep talking about the ice-free Arctic. And if you're talking from a climatological perspective, you have one view of it. But if you're talking from a habitat perspective, you have another view. So even a relatively small amount of ice that persists can be important for habitat, whereas for climate, losing large chunks of white at the pole is going to be really important.
Rick Lovett, freelance. This is for Dr. Kelly. As long as we still have that chart in front of us, if I heard you right, you said that that the seals need 50 centimeters of snow. But when I look at that chart, I'm not seeing anything over 30.
Yeah, sorry about that. Cecilia Bitz and I have a poster in the session this afternoon that gives the details of this. Basically, you only get depths of 50 centimeters of snow on sea ice where it's drifted next to pressure ridges or hummocks in the ice. What I'm actually showing you here, and I failed to explain, is these are projections of snow depths on flat, undeformed ice. We use that as the measure What we know is that it takes somewhere between 20 and 30 centimeters on the flat ice you have to have at least that much snow to form drifts of 50 centimeters or more that are necessary for the pup caves to be excavated.
Harvey Leifert, freelance. Also for Dr. Kelly, what can be done, or what might be done, for the polar bears and seals? Is there any conceivable way of live trapping elsewhere and bringing them to this refuge area, or do we just let them peter out around most of the Arctic? What is the practical implication of this research?
Yeah, it's a really good question. I would tend to discourage the idea that we could have some kind of interventions where we would facilitate transport to a refuge or something like that. I generally, it's been my experience that efforts like that, we saw a similar thing after the Exxon Valdez oil spill in Alaska in attempts to save sea otters, for example. Those kind of efforts tend to generate lots of goodwill from the public, but from a conservation perspective are frankly a waste of money. They're just not effective. So that would be my guess. Maybe I'm wrong, but that would be my expectation of that. As you probably know, my colleague Steve Amstrup had a paper out yesterday in Nature in which he and his co-authors argue that the decline in sea ice cover will essentially be linear with temperature, and suggesting that the obvious mediation is to reduce greenhouse gas emissions because it is linearly related to the loss of bear habitat.
Hi, yeah, it's Jonathan Amos from BBC News. Is there any data going back in time to look at previous interglacials to see where there may have been a preponderance of these animals? I mean, some of the fossil data suggests the polar bear has stuck around at least through the Eemian, so it must have encountered warm periods before. Where did it go? What did it do?
Yeah,
did it hunt seals? You know?
I might let some of my colleagues discuss what we know about the paleohistory of ice, but I will say that I think there's a misapprehension about polar bear survival over that period, in that polar bears began diverging from brown bears, grizzly bears, 200 to 300,000 years ago. We know that from the molecular clock. What we don't know is exactly when did they become seal specialists, okay? And that may have been in the last 20 to 40,000 years, very, very recently. This is a little difficult. People have gotten confused. If you look at the molecular divergence, you say, oh, look, they've been around for 300,000 years. But that only tells us when they started diverging, when the teeth and other traits that indicate that a polar bear is, in fact, a specialist on eating seals evolved is not clear.
Julie Brigham-Greta will be giving an invited talk tomorrow morning in an oral session where she talks about paleo aspects of sea ice distribution.
Madeline Nash, freelance. I had a question about the wind patterns. It seems like the building of this refugium is very much dependent on the continuation of wind patterns that are typical of that area today. Is there a reason to expect that they will continue to be the same or be even stronger, or what could happen to the wind patterns that would maybe not make this refugium possible?
Like basically in the Arctic Ocean, like the wind pattern will always be like somewhat similar, like what I was showing in my slide about the Beaufort Gyre, where you have a recirculation of ice in the central Arctic and the transporter drift stream. These are features of the Arctic that will always be there, but they will change geographically. Like sometime you will have a Beaufort Gyre which is much more reduced and confined to the western Arctic along the Yukon and Alaska coastline, and the transporter drift stream will be very wide, and sometime the Beaufort Gyre will expand. So these expansion and contraction of the Beaufort Gyre is something that we predict to occur. Like there will be a trend in this pattern. Like in the future, we expect the Beaufort Gyre to, in the future, be more confined to the western Arctic along the Alaska coastline. But all this means that the dominant wind pattern in the Arctic will still be from Eurasia to Canada, except that the recirculation zone would be like smaller, and the transporter drift part of it would be much wider, exporting more ice out of the Arctic, but still building ice north of the archipelago in Greenland.
Yeah, just to add to that, the pattern we've seen, we do see, if you look at the pattern of ice transport from Siberia to Canada, we do see some periodic waxing and waning of the transport, which has to do exactly with what Bruno's talking about, this expansion or contraction of the Beaufort Gyre. And the tendency with warmth is actually, overlaid on that oscillatory pattern is in fact the contraction of Beaufort Gyre, which is what part of why the ice drift from Siberia to Canada has increased in the recent period, not decreased. So there will be a trend, but the indications we have from the observational data to date indicate that's going to increase and not decrease. The other thing is that part of the transport from that side of the Arctic, over by the Chukchi and the Siberian seas towards Canada and Greenland, is also driven by a sea surface height tilt. The Pacific Ocean stands about 1 meter higher than the North Atlantic Ocean because it's quite a bit fresher. And that pattern shouldn't change. I mean, that's driven by wind patterns at the low latitudes and differences in precipitation and evaporation that may increase slightly with warming, but should not undergo a fundamental change.
This is a question from Andy Refkin, the New York Times .Earth blogger, and he's asking, given that polar bears clearly survived the Eemian warming 125,000 years ago, which was warmer than now, and given that there's not much activity even with shipping increasing in that zone north of Greenland, what realistically would the conservation strategy include other than making sure poaching is avoided there?
Well, once again, I don't think we know that the polar bear as we know it, the seal specialist polar bear, in fact survived that long ago, or had even evolved that long ago. So that's an important question that remains out there. But even given that, I guess so the other part of that question, if I got it right, was what kind of conservation strategies should be practiced if in fact this is the last stand of polar bears. And I think that's an important area. I don't think people spend a lot of time concentrating on, okay, how are we going to conserve given this is what we expect to be at the case at the end of the century. There's been a lot of focus on, what are going to be the negative impacts. But this is really a fundamental shift to a sort of thinking as, okay, well, this is the reality. Now we have to sort of start planning around that. In my experience, management of wildlife populations, you're lucky if you've got a 10-year plan. Having a 100-year plan for in a completely different habitat, that's a new territory for the resource managers, I think.
And if I could just add to the other part of the question about the local effects, as Bob showed, a lot of the ice in this region will actually be formed during the wintertime throughout the rest of the Arctic and will be transported into it. So the interconnectivity of this refuge, it's not existing there on its own. It actually is very closely connected to what happens within the rest of the Arctic Ocean. And so that's something, and it's becoming increasingly interconnected too as the ice is speeding up and it's becoming much more dynamic.
Brendan, can you comment on the human aspect of things? Like 120,000 years ago, the human population was different than now. Is that a factor too?
Yeah, well, I mean, I think it's important to recognize that, the indigenous people that live in the Arctic are the ones that are going to be bearing the real brunt of these changes, and that they're part of this ecosystem, and they have been for millennia, and these are resilient, adaptive societies. But my take on this is that the speed with which environments change has a huge implication for adaptive responses, biologically or socially, and that this is a very, very rapid change. And I'm suggesting that it will challenge both biological adaptation as well as social adaptation.
Just to be a little specific about that, The sea ice transport of sediments and nutrients is really important to establishing healthy benthic communities. So, when the sea ice melts in the spring, it creates a stratified water column because you have this light, fresh water sitting over denser water, and it's partly that stratification that allows a lively bloom of algae on the surface. They die in a few weeks or a couple of months and fall to the bottom and release nutrients into the bottom waters. In addition, sediments are locked into the bottom of the ice and are deposited, bringing nutrients into new regions. So if you shift the patterns of sea ice cover and sea ice transport, it may take years, even decades, to accumulate a new nutrient environment in which now these benthic communities can thrive.
Boston Hunt, The Economist. I have two questions. The first one, could you, one of you maybe comment some more on the Nature paper? I've just read it briefly, but it seemed to suggest that even in the worst case scenario in a century from now, about 40% of polar bear habitat will be preserved, so maybe we won't need this refuge for a very long time.
Yeah, that's a good question. I mean, I think this is a large reduction in habitat, no matter how you cut it. I think how large is an important question. It's not an entirely, easy thing to predict is how the ecosystem will sort of resort itself out and who will win and who will survive, if you will. And again, I would go back to the rate of change as being really important in that with polar bears, seals, walruses, we're talking about long-lived organisms. And the significance of that is that when we talk about adaptation in biological terms, what we're talking about is not individuals adapting, but populations adapting. We're talking about changes in the frequency of genes that match the environment, okay? And that change obviously happens from generation to generation. And what we generally think of as an adaptive response is something that happens over many, many generations. So if you have a gradual change in environment, you can get adaptive responses that will fit that. When you have very, very rapid changes in environments, adaptation can't keep pace and you tend to get extinctions. So really the question is this rate at which this environment's changing, is this more akin to sort of continental drift, that kind of a time scale, which also changed, adaptive responses, or is it more akin to a meteor strike in which the environment changes overnight? Somewhere in there is the rate at which we're changing the sea ice habitat.
I would also add that there's a lot of uncertainty in terms of the prediction, the future of the evolution of those habitat and the sea ice. So far our model have been conservative compared to what nature has shown to us. Like the decline that we've been observing in the last decade, most of the model cannot reproduce such a fast decline. So sometimes nature is actually evolving in time much quicker, and then changes occur much quicker than what our model can reproduce.
So also the Nature paper that you're referring to is talking about what happens if we mitigate, if we act to reduce our greenhouse gas emissions. And in this case, we're giving a more base case scenario of what a new Arctic reality might be if we don't. So, we're taking a look at the same, last half of the century time frame, but from different perspectives.
Okay, thank you. My second question is, you have been publishing about this before, even with the abstract in the AGU system. There's hopefully a paper about this. Could you indicate what in what you are presenting now is really new results?
One aspect that's new is the quantification of the transports from remote areas into the refuge region. So in the past, we've known qualitatively what the directions are going to be, and we've identified some shifts in the geographic regions that are the source regions as you go into a warmer world. What we've done just in the last year is to actually quantify both the base case and the changes that we've seen in the last 20 or 30 years.
And also the seasonality of the signal. Like before, like we were talking about an ice-free Arctic, but how long is this ice-free Arctic like lasting? Like during the summer, like basically what we're seeing now is that like it's an ice-free Arctic for 3 months of the year, even at the end of the 21st century. So basically, we're quantifying also like the extent seasonally of these conditions that are not very conducive for ice species.
I'll just add, excuse me, real quickly, that in terms of the snow cover, we've known for a long time the importance of this snow for the survival of ring seal pups. What's new and different is that we've had a kind of an ongoing discussion, if you will, between the biologists and the physical scientists. The Intergovernmental Panel on Climate Change models indicate that there will be a net increase of about 14–15% in winter precipitation over the Arctic ice. And that might suggest more snow accumulating on the ice. But at the same time, we also know that freeze-up's happening later, and most of that precipitation in the annual cycle falls in the autumn. And as we get later and later freeze-ups, more of the snow is going to fall into open water and not accumulate on the ice, because the ice hasn't formed yet. So the question that we answered with this work that's still showing up here is that whether the net effect of more precipitation but later freeze-ups would be greater snow depths for seals to excavate their caves or less, and the answer is substantially less, because the late freeze-up effect really dominates.
Rick Lovett again. This is for Stephanie. Which of these models, when you talk about IPCC models, so this is a business as usual model that produces the refuge?
Right. So Bruno can actually, he's the modeler in the group, he can actually address that.
Yeah, this is business as usual, like an A1B scenario. Like this is CCSM, and this is like a simulation starting from 1900 to 2100, and business as usual, which those were defined in the 1990s. So what we've seen in the last 20 years is that business as usual, as defined 20 years ago, are actually a little conservative. So we've been putting more CO2 in the atmosphere than the business as usual scenario that were defined 20 years ago. But it is an A1B scenario from the IPCC AR4 report.
So it's reasonably so it's a no mitigation, still looks as a no mitigation, close to worst case scenario.
No, the worst case are the A2s, and then like those are like, if we go even more like drastically into burning fossil fuel, these are middle of the road. I mean, there's business as usual. We could be doing worse, and we could be doing better.
And we are doing, I mean, just to emphasize again, we are doing worse. The observations are actually showing more warming and more greenhouse gases than the IPCC business as usual.
So Refuge has a follow-up question, and he says, so it's basically saying that a self-management approach emphasizing that Refuge exists, proposing an effort to give the system a chance. Is that a fair characterization? Also, there's some evidence that Rockwell Gormezano from the polar bear's southernmost front line, Hudson Bay, that bears are incredibly adaptable predators that can find other food sources like goose eggs, which is not a fatty seal, but enough to squeak by. Is that accurate?
I'll take the second question, then we'll have to come back to the first one. Andy's exactly right. I mean, the animals are adaptable. I've already talked about rates of change and its impact on adaptation. The other thing, though, is he points to the bears on land and their ability to exist there and even feed there. This brings up another issue, and we had a comment in Nature yesterday on the potential for increased rates of hybridization as bears and other marine mammals are brought together as a result of ice loss. Yes, he's correct. They might, in fact, be able to adapt to a more terrestrial existence, but there's also a lurking danger there in hybridization. His first question, maybe you could repeat that. I didn't quite follow it.
The first part?
The first part of Andy's question?
Well, he's asking if it's okay to characterize this proposal as a self-management approach, emphasizing that Refuge exists and we should give the system a chance.
Oh, I guess I would characterize it even more crudely than that, as these are sort of first steps, is identifying where a refugium would be and get people to start the conversation. The conversation, to my knowledge, hasn't really existed as to, well, how will we manage wildlife around this? It needs to happen, and we're hoping to provoke that conversation.
I mean, I think it's important to know we're a geologist, a climate modeler, an observational oceanographer, and a biologist. This is a conversation that has to include native peoples and governments in the circumpolar region and non-governmental organizations. It's a very broad conversation, and our intent, our precise intent in organizing this session, in which we've brought scientists as well as policy people and even a couple of governmental people together, is to begin that conversation that Brendan's talking about.
And there is a poster by Amy Lauren Lovecraft in the session this afternoon that is talking about policy and governance.
Okay, and he has a last question, which is, should we care? If the seal diet is truly new by evolution standards, isn't this incredibly young species in a state of flux in any case? Some losses are inevitable anyway. He knows it's an uncomfortable question, but...
Well, no, I don't think it's an uncomfortable question. I think it's a good question. I mean, you quickly realize that, you know, as an evolutionary biologist, as physical scientists, we can talk about sort of likely outcomes as we try to forecast future environments. But it's not you wouldn't want to turn to scientists, in my view, to put values on this. I mean, that's a bigger question, and it might be really different if you were an indigenous hunter in the Arctic than if you were a you know, average person on the street in San Francisco. What's the cost of losing any particular species? Again, as I said, there's also this question of rates of extinction, but I don't think we want to go there right now.
You know, as a scientist, you know, we would always say that the worst thing would be to lose the lower trophic levels, right? If what we were talking about here was extinction of microplankton, it would be a real disaster. Everything above would disappear. You know, but as a citizen, when you see these bears, which are in many fundamental ways not that different from us, being put under this kind of pressure and facing possible extinction, I think all of us have an emotional response and feel a sense of empathy, and even for some people a spiritual response. And I think in that sense it's an important issue because it raises questions for people that wouldn't otherwise be raised.
Okay, we have time for one more question.
Okay, so that's the last follow-up from Andy. He says, but a heap of scientists have signed a letter putting a value on it via the Center of Biological Diversity.
I'm sorry,
You're
can you
talking
repeat?
about the letter? This is the letter from Ken Caldera and Mark Kanan, those guys? Is that what we're talking about?
I don't know.
Well, I mean, you know, scientists are citizens too, right?
Uh-huh.
Okay, I think that wraps it up.